that the optical phonon line?
It's 26. This is located at 26.
Yeah, is that the optical phonon?
Yes.
Oh, okay.
Yeah,
He
26.
shifted back to the optimal.
Yep, no, he did. What?
Yes, he shifted.
No, I was just asking, is that, okay.
Yeah. So, because we see something interesting happen as a function of capital T, the next logical thing to do is to take zero quantum spectra, which involve Fourier transforming along capital T and little t. So this is what the zero quantum spectra look like as a function of the first time delay tau. And we see something interesting, which is that a sideband at the yellow phonon energy appears as we increase tau. And we can take a closer look by integrating the peak intensities over these dashed boxes. And what we find is that the sideband exhibits a long rise over 250 femtoseconds, which is really strange behavior in contrast to the usual exponential dephasing dynamics. And I want to emphasize that these curves reflect the dynamics of the interband coherences excited by the first pulse. So to explain the origin of this long rise, we tried to to explain the origin of this long rise, we tried to simulate the zero quantum spectra using a simple model, very similar to the one in the previous section. So we took this displaced oscillator model, which gives you ladders of states separated by the yellow phonon energy, and simplified it to an effective four-level system. And this gives us an interesting interpretation of our results. So if we look at the quantum pathways that generate the peaks in our zero quantum spectra, we see that the sideband is predominantly generated by pathways of initial interband coherences involving a vibrationally excited state. So in a way, our zero quantum spectra tags the dynamics of the vibrationally excited interband coherences by isolating them in the sideband. But unfortunately, we weren't able to reproduce the long rise that we saw in experiment. We tried different things such as varying the yellow phonon coupling strength, extending the dephasing time of the vibrationally excited interband coherences, and even simple non-Markovian phasing models such as the Kuo line shape didn't work. And we also tried incorporating the acoustic phonon dephasing from using the parameters from the previous section, but even this didn't work.
Is that figure showing that you have a positive and then negative chirp? Is that what it's saying?
No, so if I go back to the one quantum spectrum, so this is at capital T equals 0. So if it was a chirp effect, then
No, I don't mean a chirp in your laser. I mean it's what Steve said, you know, in the emission wavelength. Is the emission wavelength going one direction and coming back in a different wavelength?
no. So the emission wavelength is staying the same, but in a sense, this is
So what is the number you measured on your y-axis? Because I saw,
this is peak intensity.
oh, I thought it was.
So this is the peak getting stronger.
Oh.
So that's why the sideband appears, because as the central peak dephases exponentially, the sideband rises. So what this indicates is that the yellow phonon coupling strongly modifies the dephasing dynamics of the interband coherences. And this could be so much so, in fact, that some of the usual approximations that we make, such as the harmonic coupling approximation or the second order cumulative approximation, could start breaking down in our system. And we can try one other thing, which is to see the effect of modifying our material somehow. Specifically, we repeated our experiment on a different sample consisting of only a cadmium selenide core. And what we found is that the long rise of the sideband disappears, and the dephasing dynamics become exponential. And because the exciton confinement radius doesn't significantly change between the two samples, the main difference of this bare core sample is that the nanocrystal surface is now closer to the excitons. So this made us wonder whether the nanocrystal surface matters in the phasing dynamics on these short timescales of these nanocrystals. So we made two main observations, which is that in our core shell nanocrystals, this yellow phonon sideband exhibited a long rise over 250 femtoseconds, whereas in the bare core samples, the long rise disappears and the phasing becomes exponential. So our theory is that charges moving around on the nanocrystal surface in the bare core samples determine the local fields inside the nanocrystal that cause the energy gap to fluctuate. But in the core shell samples, the additional shell layer can screen the local fields from the surface charges, and this can allow the weaker local fields from the optical phonons to dominate the energy gap modulation that determines the phasing dynamics. And as for why our earlier simulations were inadequate, we think there could be two main approximations that could be violated in our system. The first is the harmonic coupling approximation, which assumes a quadratic potential energy surface as a function of the vibrational coordinate. And the other is the second order cumulant approximation, which only incorporates second order correlations in the energy gap modulation. So the results I've presented so far have been on cadmium selenide colloidal nanocrystals, which are the most mature colloidal material platform. So now I'd like to switch gears and talk about our results on cesium lead iodide perovskite nanocrystals, which are a brand new type of colloidal nanocrystal first synthesized in 2015. So these perovskite nanocrystals combine many of the advantages of bulk perovskites, such as strong optical absorption and emission, with the advantages of being colloidal nanocrystals. And they've also proven to have many unique and exciting properties of their own, as I'll discuss in this section. So this is the perovskite lattice structure of cesium lead iodide, where you have these black cesium atoms, polyhedra in the middle, defined by the iodide atoms, and lead atoms in the middle. And these nanocrystals are actually cubes with an average side length of 8.7 nanometers for our samples. And this corresponds to a 1s exciton transition of 650 nanometers. And to study these at low temperature, we also suspend them and have them methylonate. And here's a transmission electron microscope image of these nanocrystals, where you can see their unique cube shape. And I should mention that these nanocrystals were provided by Ano Nogueira's group at University of Campinas in Brazil. So one of the most discussed features of these perovskite nanocrystals is their unique exciton fine structure. So specifically, there was this paper published last year in Nature, which presented evidence that the exciton band edge in these perovskite nanocrystals are composed of a singlet dark state and 3 non-degenerate bright triplet states. And what's so special here is that the dark state is highest in energy, whereas in all other colloidal nanocrystal studies so far, the dark state is always lowest in energy due to the electron-hole exchange interaction. And this is because in perovskite nanocrystals, there's an additional Rashba spin-orbit interaction that lifts the degeneracy of the triplet states and lowers them in energy. And this got the community really excited because this meant excitons generated in perovskite nanocrystals could directly emit light, instead of first relaxing into and getting stuck in a dark state with a long radiative recombination time. And this also means that perovskite nanocrystals should be far brighter than any other type of colloidal nanocrystal ever synthesized. And this has been observed to be the case experimentally. But earlier this year, there was another paper where they performed magneto-PL spectroscopy on perovskite nanocrystals. And they presented pretty convincing evidence that the lowest energy state in their nanocrystals was dark. And this caused a lot of controversy in the community over the relative position of the dark state in these nanocrystals. In fact, if you look at this News and Views on this Nature Materials paper, they stated pretty definitively that their findings reveal that the dark exciton state is lower in energy than the bright state in perovskite nanocrystals. But if you look at these two papers in a little more detail, you see that the Nature paper studied cesium lead bromide chloride, and this Nature Materials paper studied formidinium lead bromide. So I think that both of these papers are right, and the difference is simply due to a discrepant difference in materials being studied. But regardless, all this controversy motivated us to study perovskite nanocrystals using 2D spectroscopy, which can provide much more concrete conclusions than single nanocrystal fluorescence.
Are these like cadmium selenide? They're strongly quantum confined?
Yes. Yeah. These are also in the strong confinement. So there's also an additional very useful property of these bitriplet states that I haven't told you about yet, which is that their dipole moments point in orthogonal directions. So to probe quantum pathways involving the different triplet states, we vary the polarization of our second excitation pulse. So here, the blue orientation is we call collinear excitation, and the red orientation we call crosslinear excitation. And here, this is what the one quantum spectrum look like for collinear crosslinear excitation. And there's a lot going on here, but what we're interested for now is what changes between the different polarizations, because that's what corresponds to the different triplet states. And we can take a closer look by taking cross-diagonal slices, and we see that the main differences between the two spectra are these peaks in the middle, which correspond to absorption and emission in different triplet states. So if we look at this collinear slice first, this peak 2 in the middle lies on the diagonal, so it corresponds to absorption and emission in and out of the same triplet state. And peaks 1 and 3 are located at plus and minus omega 2, so it corresponds to coupling between states x and y. And in the cross-diagonal slice, peak 2 in the middle is suppressed due to the orthogonal dipole moments of the triplet states. And peaks 1 and 3 show up as shoulders on two new peaks, 4 and 5, which are located at plus and minus omega 1. So they correspond to coupling between states y and z. And because we don't see any clear peaks at omega 1 plus omega 2, this indicates that the dipole moment of state y is much stronger than the dipole moments of states x and z. And an odd feature of these slices is that peaks 4 and 5 are much broader than the others. In fact, when we fit these slices to extract the dephasing rates of the individual triplet states, we find that states x and y exhibit pretty similar dephasing rates with dephasing times just over 5 picoseconds, while state z dephases much faster with a dephasing time of less than a picosecond. So our hypothesis is that in cesium lead iodide perovskite nanocrystals, the dark state actually lies between states y and z. And this model is perfectly corroborated by single nanocrystal fluorescence of nearly identical iodide nanocrystals, where they observe polarized doublets separated by omega 2 corresponding to emission out of x and y, but never a third peak separated by omega 1, which would correspond to emission out of state z. And this is because the emission is quenched by this dark state underneath. And because we see signatures of optical triplet coherences in our one quantum spectra, we should in principle be able to generate and measure coherences between the triplet states as well. And these intertriplet coherences should show up as sidebands in zero quantum spectra. So first we took zero quantum spectra with collinear excitation, but we didn't see any clear sidebands corresponding to coherences between states x and y. And this is because omega 2 is very small, so it's hard to distinguish those sidebands from the central zero mixing energy peak. But we did observe many vibrational sidebands, so I have some extra slides on those if you're interested. So this is what the zero quantum spectra look like for cross-linear excitation, where we see two sidebands corresponding to coherences between states y and z. And there being a positive sideband is an additional indication that these interband coherences are electronic in nature. And you can see that the visibility of the sidebands decreases as we increase tau, and you can see this from slices taken along this dashed line here. But from the temperature dependence, we see that the line widths of the sidebands don't change as we increase the temperature to 40 Kelvin. So this indicates that these intertriplet coherences are robust against thermal dephasing. And by fitting a slice taken at tau equals 0, we can extract an intertriplet coherence time of 1.36 picoseconds. And we perform this fit by fitting the slice to 3 Lorentzians, and we account for the asymmetry in the sidebands by adding an additional phase shift of pi/2 to the sideband Lorentzians. And this additional phase shift originates from the different combinations of dipole operators between the sidebands and the central peak. And to motivate a possible application of these intertriplet coherences, I'd like to draw an analogy to valleytronics and 2D materials. where circularly polarized values in the band structure are used for quantum information. So even though the dephasing times of 2D materials are very short, it was shown last year by Mack and his collaborators that you can actually transfer exciton polarization from one value to another with a terahertz pulse within a single cycle. So you can imagine performing similar operations on these perovskite nanocrystals where you would have linear instead of circularly polarized initialization and readout. And if you compare the inter-valley coherence time of, say, 98 femtoseconds of tungsten diselenide to the intertriplet coherence time, the intertriplet coherence time is over 10 times longer on a picosecond time scale. And because perovskite nanocrystals have been demonstrated to interact strongly when placed close to one another, perovskite nanocrystals could be a promising material platform